Okay, our basic array implementation of stacks had a defect where we required clients to provide the maximum capacity of the stack ahead of time. Now we're going to look at a technique for resolving that problem. How do we're not implementing the API. The API says we should just be able to create a stack and it should be able to grow and shrink to any size. So how are we going to grow and shrink the array? Well, first thing you might think of is when the client pushes the new item onto the stack, increase the size of the array by 1, and when it pops, decrease the size of the array by 1. That's easy to code up, but not worth it because it's much too expensive to do that. The reason is that you have to create a new array, size 1 bigger, and copy all the items to that new array. So inserting the first n items would take time proportional. If the stack's of size n minus 1, it's going to take time n minus 2 time n minus 1. So first n items would take the sum of the first n integers, which we know is about n squared over 2. Quadratic time to insert n items into a stack, that kind of performance is unacceptable for large problems as we will see many times. So the challenge is to do the resizing, but somehow ensure that it happens infrequently. So the well-known technique for doing that, called repeated doubling, is to, when the array fills up, create a new array of twice the size and copy all the items over. Then we don't create new arrays all that often. So here's an implementation of that. We start with an array of size 1. If we have a full stack, which we know by testing n, which is the number of items in the stack, versus the array length, then we just resize the array into one of twice the length before inserting the item. And how do we resize? To a new capacity, we create a new array of that capacity and just go ahead and copy our current stack into the first half of that, and then return it. And that will reset our instance variable, which is our stack, to this new bigger array. So the idea and the consequence of this is if you insert n items into an array, into a stack with this array representation, the time will be proportional to n, not n squared. And the reason is that you only create a new array every time it doubles. But by the time that it doubles, you've inserted that many items into the stack. So on average, it's like adding one operation to cost of 1 to each operation. So if you just calculate the cost of inserting the first n items, you're going to have, instead of the sum of the integers from 1 to n, you're going to have the sum of the powers of 2 from 1 to n, and that'll give a total cost of about 3n. So that's array accesses. So for the copy, there's 2 array accesses. So to insert n items, it's about 3 array accesses. This plot is another way of looking at it, which is the number of array accesses taken as you implement push operations. Every time you hit a power of 2, you take that many array accesses, but in a sense, you've already paid for them by putting those items on the stack. So that's called amortized analysis, where we consider the total cost averaged over all operations. And this is a fine example and useful example of amortized analysis to get efficiency in a stack implementation. Now what about the pop? We have to think about how to shrink the array. So you might think, well, we doubled it when it was full. Why don't we cut it in half when it gets to be half full? We don't want the array to get too empty. Well, that one doesn't exactly work because of a phenomenon called thrashing. If the client happens to do push, pop, alternating when the array is full, then it's going to be doubling, halving, doubling, halving, doubling, halving, creating new arrays on every operation, take time proportional to n for every operation, and therefore quadratic time for everything. So I don't want to do that. The efficient solution is to wait until the array gets 1/4 full before you have it. And that's very easy to implement. We just test if the array is 1/4 full. If it is, we resize it to half full. And so then at that point, it's half full. And it can either grow by adding stuff or shrink by subtracting stuff, but there won't be another resizing array operation until it either gets totally full or half again full. So the invariant of that is that the array is always between 25% and 100% full, number one, and number two, that every time you resize, you've already paid for it in an amortized sense by inserting, pushing or popping. So here's just what happens to the array for our small client example. And you can see at the beginning it doubles from 1 to 2 to 4, but once it gets to 4, it stays, once it gets to 8, it stays at that size for a while, even though there's some operations. And it doesn't shrink back to 4 until after there's only 2 items in there, and then it shrinks and so forth. So array resizing doesn't happen that often, but it's a very effective way of implementing the Stack API with an array where the client does not have to provide this maximum capacity of the stack, but still we're guaranteed that the amount of memory that we use is always only a constant multiple of the number of items actually on the stack. So the analysis now says that the average running time per operation for whatever the sequence of operations is, the average running time is going to be proportional to a constant. Now, there is a worst case, that is at the point when the stack doubles, it takes time proportional to n. So it's not quite as good performance as we might like, but it's what the advantage that we get is very fast pushes and pops, just access array and increment it, and very efficient for most operations. And for many, many clients, that's an effective trade-off to make. So what about memory usage? Well, this is the analysis of memory usage for stacks, and it's actually less memory than for strings. The amount used is between 8n and 32n, depending on how full the array is, and just a quick analysis of the amount of space that arrays take in Java. So again, this analysis is just for the stack itself, not for the strings which the client owns. So what are the trade-offs between using a resizing array versus a linked list? Those are two different implementations of the same API, and the client can use them interchangeably. Which one is better? In many situations, we're going to have multiple implementations of APIs, and depending on properties of the client program, we're going to have to choose which one is the better one to use. So for linked lists, every operation takes constant time in the worst case. That's a guarantee, but we have to use a little extra time and space to deal with the links. So it's going to be slower. Resizing array implementation, we have a good amortized time, so total averaged over the whole process is good. We have less wasted space and probably faster implementation of each operation. And so for some clients, maybe that makes a difference. Perhaps you wouldn't want to use a resizing array implementation at the moment that your plane's coming in for a landing. You wouldn't want it to all of a sudden not implement some operation quickly. If you need that kind of, or maybe in an internet switch where packets are coming through at a great rate, you wouldn't want to be in a situation where you're missing some data because something got slow all of a sudden. So that's a trade-off that the client can make. If I want that guarantee, if I want to be sure that every operation is going to be fast, I'll use a linked list. And if I don't need that guarantee, if I'm just care about the total amount of time, I'll probably use the resizing array because the total will be much less because individual operations are fast. So even with these simple data structures, we have really important trade-offs that actually make a difference in lots of practical situations.